Yeah, you just substitute that for dry lab 6. Okay, so what's a chemical equation? You have a set of reactants. Reactants. That's what you start with. Now, if you can combine the reactants together to form a more stable arrangement, they go to products. Only if it's more stable. And usually it gives off energy. Now, if you're trying to force something to become more unstable, that requires energy. Okay? So when you go from unstable to stable, you give off energy. When you go in the opposite way, it requires energy. And you see this in chemistry, physics, geology, biology all the time. For example, the last thing I teach in my organic biochemistry class is what happens in your body when we metabolize glucose. Some of the steps are unstable, so it requires energy to move to the next step. Even though eventually you end up giving out more energy. Okay, so this is important now. Okay, and the reactants are atoms or molecules. Products are atoms or molecules. Not the same though. So what's going on with this arrow here? Okay, when the arrow happens, the reactant bonds are broken.
Sorry, what are the products? There's nothing after products. The arrow. You see products right there.
Yeah, do you see the ditto marks?
Oh.
Okay, so when the reaction starts, we have to break apart the bonds on the reactants, and they're all separate. And those form something called the activated complex. The activated complex is a mishmash of all the atoms from the reactants. Okay, now this is what is kind of confusing, is with the activated complex, this bundle of atoms ready to become more stable, they do one of two things. They either form a product or they fall back to become a reactant again, which is very strange. Most people don't realize that. And when a reaction happens, some of it goes to products, some of it comes back to reactants. In fact, there's a whole unit in 1A and 3B that talks about equilibrium, and that's what that is. When that all stabilizes out, creates an equilibrium. And it's a huge topic in chemistry. Okay, so basically we have unstable reactants form the activated complex, produce products, plus energy. Okay, so what we're going to look at now is a fancy way of saying all this. We're going to graph potential energy against reactions, against reactant potential energy versus product potential energy. Now, potential energy. There's two kinds of energy, potential and kinetic energy. The more potential energy something has, the more unstable it is. Okay? So the more potential energy, the more unstable it is. Now notice on this graph, the reactants are higher than the products. That means the reactants on this graph have more potential energy than the products on this graph. So to become more stable, we've got to put energy into the system to break apart those bonds in the reactant side. So we're putting energy into the system. In other words, if I have a match, it doesn't spontaneously burst into flames. What do we have to do to get the match to burst into flames? Strike it with a spark. Just like when we try to get the Bunsen burners going, you have to have a lighter, right? Or something to create a spark. That's the energy. That gets us up here. That's where the activated complex is. High potential energy. So now that activated complex is going to form products, or it's going to come back to reactants, because the activated complex is more unstable than either the reactants or the products. Now, it depends on how high the energy is required to get the reaction going. Like, let me give you two examples. Who's heard of TNT? It's called trinitrotoluene, okay? It is very, very unstable, meaning that the energy to get it going is very, very small. You could just bump it and it'll explode. But if we take something like gasoline, can you bump gasoline and make it explode? No, it takes a spark, it takes some energy. Otherwise, it does nothing. TNT. So gasoline's energy requirement to get going is much greater than TNT's energy requirement, which is very little. And that depends on the height of this. That height is called activation energy. How much energy is required to activate the reaction, to get it moving? Let me give you another example.
That's from the bottom of the reactants to the top back here.
Yeah. Yeah. Now, I'm going to give another reaction. Carbon and diamonds. What's the diamond made out of? Carbon. What's charcoal made out of? Carbon. What's the difference between the two? Thousands of dollars, right? Okay, guess which one's more stable, charcoal or diamonds? Charcoal's more stable. So you got a ring on your finger, big fat engagement ring. Guess what that's going to do over time? It's going to go to the more stable form of carbon, which is charcoal. You're going, what? How can that be? I have my grandmother's rings were diamonds and they look just fine. The difference is the speed at which that transformation happens. It happens to be very slow. So the activation energy going from diamonds to charcoal is huge. That's why it happens so slowly. So the height of the activation energy determines how fast something will go. If it's low, it goes fast. If it's high, it goes slowly.
Charcoal used to be diamond? In the process of making charcoal, it used to be diamond? Charcoal?
No. Charcoal is just around. Diamonds are formed from charcoal under great pressure because activation energy is so high. That's why it takes all that energy to get over it. And then going the other way, it's a lot too. So that's why it goes slowly into the point where we're talking millions of years. So if your diamond's around in a million years, it'll look like charcoal. But if it's less than that, it looks like a diamond. Okay, it's a reaction. Unstable to more stable. Activation energy determines how much energy you need to get it going. It's all it is for all chemical reactions, no exceptions. Now, remember I said reactants to products plus energy. So this difference is the energy given off. And that's usually in the form of heat. So when you burn gasoline, it gets hot. When your diamond goes from down to the carbon, it gets hot just a little bit. Okay. So this discussion so far, it's just to get you acclimated to what's going on at the atomic level. So let me give you some examples of chemical reactions. There are two principles that need to be followed. Okay, one is conservation of mass. If you start with 5 grams, guess what you end up with? 5 grams. Otherwise, we have something called an explosion. E is equal to mc squared. So if you're losing mass, it's because it's converted to energy. And energy produced from mass is a horrendously large amount. So conservation of mass, what you start with, what you end with. 5 grams starting with, 5 grams of reactants, you have 5 grams of product. The problem with that statement is the new molecules formed don't weigh the same as what you started with. Number 2. Conservation of the number of atoms. So if you start with 5 carbon atoms, you end up with 5 carbon atoms. That's what I mean by that statement. And these drive the universe. And just remember that energy and matter can be interconverted. E is equal to mc squared. That's what that equation means. Okay, so if we have less mass than we start with, it's got to be in the form of energy. Okay, so let's look at a chemical reaction. Let's take methane. I'm going to burn it in oxygen. To create carbon dioxide and water. This is called what you do at your Bunsen burner. Okay, conservation of mass. Okay, that is a general equation. We don't know what mass we're starting with or ending with. But number 2, conservation of the number of atoms. Okay, what are the 3 atoms we have in that reaction? Carbon, hydrogen, oxygen, right? So the number of carbons have to be the same as what you start with, what you end with. Hydrogen, hydrogen, oxygen, oxygen. That's what I mean by the conservation of the number of atoms. So the first thing we're going to do is an inventory. We're going to inventory the reactant side. We're going to inventory the product side. The reactant side, how many carbons do we have in this reaction? 1. How many do we have on the product side? 1. Looking good. Now, a few little bookkeeping things here. There's a number out front here that is not listed. That's because it's 1. So if you like to go in on your equation and put 1s there, that's fine. So you're consistent. Normally, chemists don't put 1s there. Okay, let's continue with the inventory. How many hydrogens do we have on the left? 4. How many on the right? 2. Got a problem. How many oxygen on the left? On the right? 3. We have some from the carbon dioxide and some from the water. You have to add them together. Two oxygen.
Oh,
Now, is this balanced? No, we have not conserved atoms. So we've got to futz with this thing. Now, you can change, there are 2 numbers in this equation. There are coefficients and subscripts. You cannot change the subscripts. No exceptions. Those are off limits. What you can change, though, are the coefficients. Okay, so let's work on the hydrogens. What can I change coefficient-wise on the left or the right so that the hydrogens are equal? Let's put a 2 out in front of the waters over here. That gives us now 4 hydrogens. But look what it does to the oxygens. How many? It also changes the number of oxygens. How many oxygens do we have? 4. Okay. What can we do to the oxygens to make them equal? Okay. That gives us now 4 oxygens. So the inventory for the reactant side is equal to the product side. Now, I've seen this taught a whole bunch of different ways. No one talks about inventories of reactants and products atoms. People sometimes teach it like this. Well, let's just put a number there, see what happens. Now, I have not done one analytical thing here other than take an inventory. That process is called guess and check. So you guess a coefficient and then you check it via an inventory. You always have to do an inventory because unless these numbers are equal, this equation is not balanced. It's not valid at all. Now, the first step in stoichiometry is to balance the equation because everything depends on that balanced equation. So you don't balance the equation correctly, the whole problem is wrong. Yeah. Okay, so two waters. Yeah. Okay.
Oh, yeah.
You get it.
No, actually.
Yeah, you're thinking the right way. Okay, are there any questions about that process? Okay, so let's try another one. Can you have half of a molecule? No. So the coefficients have to be integers because the coefficient refers to the number of molecules. So this equation says we have 1 methane combines with 2 oxygens. That's what that left side says. The right side says 1 carbon dioxide is produced and 2 waters are produced. You can't say half a water is produced or whatever. So if our balancing the equation requires a fraction, that's okay. You just can't leave it that way. So I'm going to show you one in a minute here, which requires a fraction. Instead of methane, let's use ethane. When you burn ethane, you also produce carbon dioxide and water. So we have the same carbon, hydrogen, oxygen. Okay, carbons on the left, we have 2. Carbons on the right, we have 1. Automatically, or already we have a problem. Hydrogen, 6 on the left, 2 on the right, 2 oxygens on the left, 3 on the right. Okay, remember now, coefficients out front here.
Like coefficient for a compound, like for the second element.
So it's a 1. It's a 1 then. If there's no coefficient out front, that means it's a 1.
No, I get that. I'm just saying that you can't put the coefficient in front of the O because it's a compound.
Oh, yeah, it has to be out in front and it applies to the whole molecule. Right, right, exactly. Okay, he brought up a good point. When you put a coefficient out there, it applies to the whole molecule because it says two of them. Going back up here, this says there are two waters, not two oxygens only. It says two of the whole thing. Okay, so the coefficient applies to the whole molecule. The subscript applies only to that atom. Okay, so let's fix this. Where do you want to start? Bless you. Carbon, okay? We put a 2 here. That kicks our carbons up to 2. Oxygen's affected, right? So we have 4 oxygens and 1 oxygen. So that's 5 oxygens. And we're here up to 5. The oxygens are coming from 2 separate molecules. Okay, we're still not done. So we want to work on next, hydrogens or oxygens?
So it's 5 because there's already 3 oxygens, but because we put the 2 on the coefficient and we put it as 5. Okay.
And you have to add all of them on the one side, even if they're in multiple molecules. It could be in 5 molecules. Doesn't matter. You have to add them all up. Okay, so what do you want to work on next? You can start with anyone. Now, your point is, where do you start? What I would recommend is you start with the most complex one as opposed to the simplest one.
So complex is like the variation of the numbers, like what define complex?
Just on how many atoms are involved in the molecule. Oxygen, how many molecules? Oxygen gas, O2. How many atoms are involved there? Just 2 of oxygen, though. It's just oxygen. When we changed water or carbon dioxide, we changed not only the hydrogens, we also changed the oxygens.
Right. Okay. How do I tell what's more complex, like CO2 or C2H6?
Well, definitely the oxygen on the left is too simple. Then let's just look at the carbons or hydrogens. But again, it doesn't really matter which one you start with, because when you finish the inventory, after you balance everything out, regardless of which one you start with, you'll still end with a balanced equation. Okay, so how about if we go hydrogens? That's what we did last time. Okay, so what do we do to the water over here, coefficient? 3. Okay, that kicks our hydrogens up to 6. And oxygen Y is going to be changed. So we have 4 here. And we have 6 there. You guys, is that right? No. You have 4 oxygens and 3 oxygens. See, this is 3 times 1 is 3. So we don't have 10, we have 7. Okay, carbons look good, hydrogen looks good, oxygens don't. So what are you going to put for the coefficient in front of the O2?
But sorry, why is it, wouldn't it go 5 to 8? The oxygen would go 5.
How'd you get 8? Yeah, but over here is 4 on the carbon dioxide. Right? 2 2s, 4, 3 1s.
Right, yeah. Yeah.
Okay, so what are we going to do on the left? Huh? Two times what is 7? Not adding, times.
Oh.
2 times what is 7? 3.5. Ah, who said that? No fractions, right? Okay, but it's balanced though, okay? Eventually we have to end with a whole number, right? So now we have to fix it. Yeah. Yeah. Okay, one approach is to do, instead of starting with carbons, let's put another number in for carbons and see how it flows out. Remember, guess and check. Guess and check. Now, we're at the point here where the thing is balanced. It's just that we can't have a fraction in there. So this is a technique to clear fractions. How can we rewrite 3.5 to be an improper fraction? Yeah. Perfect. Let's hold that thought. Okay, 3.5 is the same as 7 halves, right? Now, repeating what he just said, now what if we just double everything right now? What's going to happen? Well, 2 times 1 is what? 2. 2 times 7 over 2 is what? 7. 2 times 2 is 4. 2 times 3 is 6. And because we multiply everything by 2 with it already balanced, it has to be balanced first for this to work. You just multiply everything by 2, and that clears the fraction. Now it's balanced. If we take the inventory, we have 4, 4, 12, and 12, 14, 14. No fractions. Now, some people teach it a little differently about the fraction bit. They'll say, stop, we cannot do fractions. So they'll say, let's go ahead and go back to the very start. Instead of saying 1 ethane, 1 C2H6, let's just start with 2 or 3 or 4. And if you go through and check reactants and product atoms, okay, the approach I use is similar to a lot of people's approach. The door's open. It was locked. Okay. So this takes practice. If you've never done this before, you need to do a jillion of these. That's what the dry lab next week is all about. Practicing balancing equations. Now you're going to be overwhelmed when you see the number I have in that worksheet. There's a lot of them there. And if you already know how to do balancing equations, because I provided the answers as well, you can go ahead and do maybe every 4th one or something like that. But if you've never done this before, and secondly, I've got 2 other worksheets there to practice. Okay, dry lab number 6 equations. I've also got equation balancing 1, 2, 4. So there are 4 worksheets there. The one required for the dry lab, though, is right at the top. It says dry lab 6 equations, okay? So let me repeat The dry lab next week, dry lab 6, is to be done via this file, not the one in your lab packet. Second one down. All right. So what I want to do now is for you guys to start practicing this. And then towards the end, towards like 10 till, I'm going to show you one more technique. So what we're going to do is, okay, so now you can jump around if you want. Do not do number 9. 9 is the hardest one on the page. That one I'm going to show you a little trick that'll help you do that problem. Okay, so let's practice this. And again, don't underestimate this. This is the first step of doing stoichiometry. It's crucial that you understand how to do this. That's a good start. Have you done this before? Did you see the email I responded to? Yeah. Yeah. And so forward that now to the person that I think Kathy Snyder is her name.
Yeah.
Yeah. So send that. Why don't you do it now, just so she has it?
Oh, what would you like me to do?
Hmm?
What would you like me to do? I like just double check.
Forward my response to your email to her,
Oh, forward. Okay.
because she wanted to know the date, which is the first day of class. You see, you're dressed for the cool weather we're going to have. You can do it that way. Only on the left you have 1, not 4. That's fine, but just, you don't have 4, you have 1. Yeah. Right, but if you group it together like you did, that's fine. But you treat it as a group. So how many groups of sulfate do you have? 1. Hmm? Yeah. Just like this is a group, right? Because of the parentheses.
Yeah.
It doesn't break apart because it's on both sides of the equation. So that means it's not broken apart. You have 3 of those, and you have 1 of those. Like if you put a parentheses around that with a 1, you'd have 1 of them.
It's not balanced.
Yeah, you're doing fine. Just keep at it. Okay, so you have a problem with the iron, right? So we're going to put over here for the iron. Okay, so update your inventory. If you keep updating your inventory, you know where you are. So, yep, hydrogen is the same. That's fine. Let's look at the sulfate now. You have 3 over here, 1 over there, right? Okay. That changes the hydrogens too. That makes it 6 now instead of 2 and 3 there.
It's like a plus.
Not yet. You have 6 over here. So, and then how can you make 6 hydrogens over here? 3 there, right?
Yeah.
You're done because they're equal. Excuse me.
Okay.
That looks good.
So bomb.
I mean, I like peanut butter and jelly.
They have no one's over.
They have different flavors, I presume.
They have one.
I like Nutella better. Well, you got some numbers that are off, right?
Yes, and they need a balance.
Yes. Now, over here, you have 3 SO4s.
Oh, I do. Wait, so what's an S?
Not 4?
No, the 4 oxygen.
Yeah. So in the group SO4, it wants 3 of them. So it's SO4, SO4, SO4. So how many sulfurs do you have?
3.
3, not 1.
Oh,
And how many oxygens?
3. Wait, did they multiply?
Right. Okay. Well,
Right.
this is sulfurs are, right? This is
Yes.
1. That's 3. So if you put a 3 out front of this, okay. So how many hydrogens do you have now?
5.
6.
Because you multiply that time.
Because you have 3 H2SO4s. H2, yeah, each time. So
Okay.
that's,
So then this would be 6.
Mhm.
And then you,
And so you've got, how many over here now?
oh,
2, right?
wait, 2.
You have 1 H2.
Yeah.
That's 2 hydrogens.
Oh, now you multiply.
No. Cross it off. Your initial inventory should have said 2, not 1.
Oh, because there's 2.
Yeah,
So
exactly.
I was saying that there's 1.
Mhm.
Okay.
You have 1 H2.
Yes, but makes it 2.
Yeah.
Okay.
Okay, so now we have 6 hydrogens here, but only 2 over here. How can we change? Yep, okay. Cross it off, put a 6.
6.
So you always do inventory, because you always,
Okay.
that way you know where you are.
So if there's 2 here, can we keep that? Or do we have to multiply? And then
Is it 1 there?
No, it's 2.
2. Is that a 2 there?
That's a 2.
Oh,
Sorry.
okay. All right. And you have 1 over here. So what can you do to this? Yep.
Oh my God.
Here. Now,
It's a B.
Look at the S's now. You have three S's over here,
Mhm.
and you have how many over here?
1.
Times 3 is what? 3.
So you just, and then this would be times 3. So then you get 12. Oops. Isn't that like a little shortcut? Just
Mhm.
multiply everything.
Well, it's not a shortcut, but it's just,
What you do.
yeah. And if you keep taking inventory, you know where you stand.
Okay.
That's real important. In a lot of places where you read how to do these, they don't say that.
Okay.
Inventory all the time. And they also like to put the letters over here. Some people put the letters here and here.
Okay.
I just put them once. So
Yeah.
this is
It makes so much more sense.
it's busy work if you put. Now, unfortunately, this method is called guess and check.
That's a check.
Yes.
Have to hope for the best. You go with it.
Yes, and that's correct now, by the way. So
Thank you. You want to do number?
okay, so put on your inventory here. The FEs, the H's, the S, and the O's. S and O's. So how many irons do you have? 2 times 1 is what? 2. And you have one F2 over here, right? So 2 and 2 then. Talking about S's. So are you doing this by SO4s or by S's and O's? How did you get these numbers over here?
I got S and O's, but I just realized that this is just like L.
Okay, but there are 3 S's here, 1 S here. However, when you multiply this whole thing by 3, that gives it 3 S's over here. 3 S's over here. Do you see how I got the 3 S's on the left? Okay. So 3 and 3. Okay.
Yeah.
Mhm.
So it was.
Yeah. Now you know it's balanced. Because if you didn't do that, you couldn't tell whether it's balanced or not. Well, I'm glad you're doing it in your head. Because most people can't do it in their head.
It's just like math. I love math. A lot of people hate
The only
math.
problem is math when it's not math. Normally in math, you have a process for solving it, like in algebra and stuff. See, this is guess and check. It's not.
I got it now.
It's making sense.
This one, what's that? Is that?
It is right. Yeah. See your inventory. You know from your inventory it's correct. 226633.
I was confused if 4
Right.
is part of the.
Yeah. So what the parentheses means is there are 3 SO4s. SO4, SO4, SO4. That's why there are 3 S's. And then there are 12 oxygens, though, not 6.
12.
Each SO4 has 4, and you have 3 of them. So 3 times 4 is 12.
Wait, now I'm confused.
See, the 3 means there are 3 groups of SO4s. So you have SO4, 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 4, 4, 4. That's how you get 12.
Oh, so I times by 3. But
So are you doing this by the groups? Oh, okay. All right. Then don't do it the way I was just telling you.
Okay.
I'm going to show everyone about grouping in a minute here. So you start with groups right from the beginning. That's really good. So you're fine. And the point I was making though is unless you show the inventory, there's no way to show that it's balanced.
So I can't show my phone.
It's okay. You're fine. Go to the next one. You're welcome.
2 times 1 equals 3.
1.5.
So, but multiply 1 half 2. So it'd be 4 over 2.
3 over 2.
So this would be
And 3 over 2 times 2 is 3.
Oh, okay. And this would be 3 over 2? Yeah. Oh, wait.
Okay, how many carbons do you have over here?
2.
2.
1.
So if you multiply 2 times that, you have 2 carbons,
Oh.
not 3 halves.
That's not what we want to do.
Hmm?
That's not what we want to do, right?
Right, so go back, put 2 back in there.
2 back in where?
In front of the,
Oh.
didn't you have 2 there before?
No.
Oh.
Oh, thank you.
I thought you did. This makes sense? Now, did you do that lab there?
Finish it. I'm working on it still.
Okay. Because I reassigned another lab in place of this, so don't do any more.
Oh, so there's this one we're not doing.
We're doing another one in its place on equations.
Oh, why?
This doesn't give you enough practice. Where the one I gave you gives you not.
Online?
Yeah, you go to files and it'll say dry lab. Unit 3.
Periodic table bonding?
Yeah. And go to the top.
Online?
Oh, wait a minute. I need to do,
Equation balancing extra credit.
no.
Equation
Let me sync it. I need to sync. I forgot to sync it. Hold on. I forgot to sync. Yeah. Yeah, see, there's a master file called blueprint, and I modify that, and I sync the blueprint to each lab section. But if I forget to sync, what I change, you wouldn't see it. So that's what I just did. Okay, you should see it now. Yeah. Mm-hmm.
Oh, whoa.
Lots of practice.
Print this, would it be?
It'll be on one page. But I recommend not printing it though, because it's going to be really tiny. Huh?
And turn it in also a notebook?
Yeah,
or...
exactly. All right, so let's go over some of these. Now, there are 2 ways to do problem number 1. And some of you did it intuitively. Now, What did I leave off? What?
Yeah.
Water? Okay. Oh, all right. Okay. Now, one way to do it is by writing down those and do an inventory. Now, there's another way to do it. It's very similar to this, and it's a little less cumbersome. Okay, so we have SO4 is called sulfate ion. It's a group, SO4. Do we have SO4 on the left also? We do. So we're going to start by grouping them and keeping them together. So instead of SO here, we're going to have SO4s. So the only way this will work if there's one on each side, no exceptions. Both sides have to have a group. And it's usually an ion group. Could be OH, SO4, SO3, NO3, CO3. I mean, as long as it's a group from your common ion chart, this technique will work. Okay, so how many SO4s do I have on the left? 1. How many on the right? 3. H's, I have 2. H's over here, I have 2. Irons, I have 2 and 1. Okay, so where do you want to start? Fe. What about SO4s? How can we make 3 SO4s on the left? Times 3. And that also brings up our hydrogens to 6. So our irons work, our sulfates work, hydrogens don't. How do we fix it? 3 on the right. Done. Now, you can also do this by separating out the S's and the O's. Works just fine. It just takes you longer to do it that way. Okay. Now, the second one is exactly like the example I gave before we started this practice, using the ethane, oxygen, CO2. And that had a fractional coefficient that you had to fix. All right. So I'm going to stop here. And I want to remind everyone that I'm substituting the dry lab number 6, Monday, Tuesday, for this file here instead. In lieu of it, yeah. Dry lab 6. Okay, so does that make sense? We're doing this one instead of the one in your lab packet. It's similar, but this one will give you more practice. And I want to emphasize this is the first step of stoichiometry. If you mess up the balancing equation, your whole probably not good. There are 4 steps to stoichiometry. Step 1 is balance the equation. Step 2 is what's given, what are you trying to calculate, and the setup. That's going to be like unit 1 with a little bit extra stuff in it. Now, for those doing lab today, you're only going to be doing the lab. You're not going to be doing the calculations because we haven't got far enough into the lecture so you understand what the questions are. Okay, so we're just doing, do the lab, take the data, and you're done. And then when our lecture catches up, which won't be long, then you can finish it and submit it. Okay? All right, that's it for today. And for those that don't have lab today, have a good holiday. Stay cool. I'm going to be sweltering tonight at a baseball game in 111-degree temperature. It's supposed to arrive today. I know it's a little tight, but